Hello everyone, I hope you're doing well wherever you're watching me from. Today I want us to do this paper, practical, that is Physics Paper 5, 0625, Cambridge, February-March 2022. So there has been request that we do some practical on spring, how the spring stretches. So we're going to start with this. Now, as I always mention, the very first thing when you're given a physics practical, the very first thing to do is always to go through the question paper and understand what exactly the question wants. As you're going through the question paper, as you're going through the question, you will also notice the apparatus that you need to have on your table. Because you are aware that IGCSE physics, there is no list of apparatus. The apparatus are always provided, but then you confirm as you are going through the question. So let's start. So in this experiment, you will investigate the extension of a spring and use it to determine the weight of the meter rule. The spring has been set up for you. Carry out the following instructions. So we have figure 1.1, as you can able to see, the spring is there. And then figure 1.2, there is a load that has been put there. That is the diagram you can able to see. So we are being told to set up figure 1.1, and then part A, measure and record the unstretched length L0 of the spring, as shown in figure 1.1. Suspend the 1.10 Newton load from the spring, as shown in figure 1.2. Measure and record the unstretched length LS of the spring. So part B, suspend the meter rule from the spring using the hook fixed at the 95.0 centimeter mark, as shown in the figure 1.3. Place the other end of the meter rule so that the 5.0 centimeter mark of the rule rests on the pivot. The meter rule must rest on the pivot at the 5.0 centimeter mark throughout the experiment. Place the load W, which have been given and is labeled W, on the meter rule with its center at a distance D is equal to 20.0 centimeter from the pivot. Ensure that the meter rule is horizontal by adjusting the clamp that holds the spring. So the diagram is there. So we continue to read the question so that we understand. Maybe there's a part that we're supposed to do practical. That's why you need to read all the questions. So measure and record in table 1.1 the stretch length L of the spring as shown in figure 1.3. Repeat this procedure for distances D for 30 centimeter, 40, 50, 60 centimeter from the pivot. We have the table that you've been given there, which is called table 1.1. We are required, after collecting data, to plot a graph of L in y-axis against D in x-axis. Start the axis at the origin. Question 1 related to the graph, D Roman 1. From your graph, determine L, the value of L when D is 0.0 centimeter. Roman 2 of D, calculate WR, the weight of the meter rule, using your value of L from D Roman 1. The values of L0 and LS from A and the equation that is given below, which you can able to see. Part E Roman 1, it is sometimes difficult to position the load W on the scale of the meter rule at the correct distance D from the pivot. Suggest one change to the apparatus to overcome this difficulty. Roman 2, suggest one possible source of inaccuracy other than the difficulty described in E Roman 1. Assume that the experiment is carried out carefully. Now that we have gone through the question, we understand that the experiment that is supposed to be done is only as we have described. in page 1, and then we record them in table 1.1. After that, it is just doing analysis. The reason why I still insist that you have to read the whole question is that sometimes you may think that you are done with carrying out the experiment, and then you end up dismantle the apparatus that you've been given. And then you only realize later on that you are supposed to maybe take another measurement, maybe in part E. And once you have dismantled the apparatus, it becomes difficult or take your time again to put them the way they were initially. So let's start the experiment right away. So here we have the spring. That means the distance B from here is 5 centimeter. This is at 95 centimeter. So if we want to start with the B, distance B, which is 20 centimeter, that means we need to place this mass W at 25 centimeters, so that we have, so we place this at 25 centimeter, and because it is slotted mass, that means I'm able to see exactly. There is the long line, I can able to see it through. That is the advantage of using slotted mass. And because of that, there is extension. So the spring has extended, but we don't know whether it is horizontal. So it is good if we can take some shock measurements to confirm. So this is at about 22.4. I also need to check that this side is at 22.4. 22.4. Yeah, that is correct. Now the next time is now to measure the length. Measure the length. So now we have data, and from this data here, now we're going to use the data to plot the graph. So before you plot the graph, you need to know the range. From D, what is the lowest value? We have been told to start from 0, 0. That means the lowest value of D is 0. And for L, value of L will also start from 0, and the highest is 4.5. So we need to start that, having that in mind. The very first thing is to start by labeling the graph axis. So that is L in y-axis, so that is L, which is in centimeter, and D is here in centimeter. Labeling of axis, there's a mark for that. So we need to identify the scale that you're going to use for L and for D. Let's start with D. So remember the kind of scale that we're choosing, it should be where our graph can able to occupy at least 3/4 of this page. So let's look at D. If you're supposed to start from 0, and then the lowest value is 0 and the highest value is 4.5, so we just need to check how many divisions we can able to use. So we have these small divisions here, so we can have 2, 10, so that we can able to have here 1, 1.0, 2.0, 3.0, 4.0, 5.0, yeah. So 1 unit here represents small 10 boxes. And then also this side for L. So for L we have 0 to 60, so we need to check if we can have the small boxes, 10 of them representing 10 centimeter. And if we do that, we'll have this here will be 10, another 10, that will be 20, 30, 40, 50, and then we have 60, the last year, 60. All right, so now we can able to start plotting our points. Remember, no matter how your values look like, whether you feel that your neighbor has the best results, please always use your values. Always use your values. So we start 0, 0 is here. We mark that with a cross. Then 2.9. We just made a mistake. So this is D. D is this. So I'll just remove this. Or let me just cross here. So write 1. Those mistakes are there, but now we use it. So now at 20, we need 2.9 for L. So 2.9 for L, so 20. So this is 3.0, 2.9 will be here. So here's my points. So we'll able to ignore the one that we had noted. So we'll able to use this. So we need to draw a line of best fit using our values. Now, if you want to know whether your graph is a straight line or a curve, look at the question that is following. For instance, from your graph, determine L, the value of L when D is 0. So when D is 0, we expect a value that is along this line here. If you look at our points, the points are not starting when D is 0. The points are starting, at somewhere here. So if it was a curve, we cannot able to extend a curve. So by us expecting us to find the y-intercept, it gives an idea that we expect, or the examiner expect, to see a straight line cutting the y-axis at any particular point where we are going to find. Now, I'm going to tell you why I've decided to use this point. Of course, if you want the best line or best fit, then these 3 points could be the best. But interestingly, if I use this, I have foreseen something. We are supposed to use your values, but then there's an advantage of reading this, because sometimes experiments don't work the way you expect. Now, we expect that the value of L here, minus L naught, and remember our L naught was 2.0. What does it mean? It means this value of L should be greater than L naught. If I draw this using these 3 values here, the value was going to be less than 2, and I was going to get a negative. So I have used this to draw my graph, and so therefore I start answering. So this passes through, this is 2.15, you can round off to 2.2. So that is 2.2 centimeter. Then we come here, and then we use that to do our calculation. So calculate WR using this formula. So from here, WR is given by 2 into 2.2 minus 2.0 all over LS. So LS is here, that is 3.1 minus 2.2. So using our calculator, then you're supposed to multiply this by K, and K is 1, so that is 1.0 newtons. So you can able to see clearly that these, they are in centimeter. So once we cancel the centimeter, that means our unit should be in newtons. So from my calculation, I get 0.44 newtons. 0.44 newtons.